All right, so let's do some derivatives of natural log functions. So these examples again are from your textbook. So the first one, we have f of x equals the ln of the sine squared of x, and we want to find the derivative f prime of x. So note that my function is not just the ln of x, but it's the ln of a function of x, sine squared of x. So when I take the derivative using the shortcut rule that I just derived for the derivative of ln x, I'm going to take 1 over that argument of ln, whatever that is, but then I have to multiply that using the chain rule by the derivative with respect to x of that argument, whatever it is. Okay, so in this case, what goes into the box is sine squared of x. So my f prime of x is 1 over sine squared x, the argument of the ln, times the derivative with respect to x of sine squared x. So 1 over sine squared of x I can leave. The derivative of sine squared of x, remember sine squared of x is sine of x squared. So I'm using the generalized power rule there. I'm taking my power down in front, times my base function sine x to 1 lower power, which is to the first, times the derivative of sine x, which is cosine x. Now, if I'm thinking carefully, I realize that my sine x here, which is really in the numerator, can cancel with one of the sine x's in the denominator. So what I have for my f prime is actually 2 times cos x over sine x, or I could write that 2 times cotan x as well. All right, let's look at the next one. Here we have ln x raised to the 1/5 power. So the fifth root of ln x is the same as taking ln x and raising it to the 1/5 power. So to take the derivative f prime of x, this I want to look at as a function raised to a constant power. So to take the derivative, I'm going to bring the power down in front. I'm going to raise ln x to 1 lower power. Let me just write it out because maybe we haven't seen this lately. Times the derivative of ln x, which is 1 over x. I'm taking the derivative with respect to x. So my f prime of x then is 1/5 times ln x to the negative 4/5, that's 1/5 minus 1, times 1 over x. And again, I could also write this as 1. Now, the 5 and the x can be in the denominator, and so can ln x raised to a positive 4/5 power. So that's another way to write it, and one is not necessarily better than the other. All right, and then last but not least, number 18. So wow, this is a pretty big one. Let's see if we can work our way through it one step at a time. So y prime here, or dy dx, I have an ln of 1 plus e to the x all squared. So I'm going to first bring my power down. I'm going to raise my base function, ln of 1 plus e to the x, to 1 lower power, which is the first power. And again, I don't really need to write that, but just to make it extra clear. And then I have to multiply that using the chain rule by the derivative of the ln of 1 plus e to the x. All right, so my y prime is 2 times the ln of 1 plus e to the x, and then I have to take the derivative of ln of 1 plus e to the x. So I can kind of look at this similarly to what I did with number 4 with my box notation. To take the derivative of the ln of a function of x, I have to put 1 over the argument of the ln times the derivative with respect to x of that argument. All right, so I'm almost there. My y prime is 2 times the natural log of 1 plus e to the x times 1 over 1 plus e to the x times the derivative of 1 plus e to the x. The derivative of the added constant 1 is 0. The derivative of e to the x is itself. Now again, what's the simplest way to write this? Well, I would say probably 2 e to the x times the ln of 1 plus e to the x, that's all stuff in the numerator, divided by 1 plus e to the x is the only stuff in the denominator. All right, so we've used now implicit differentiation to derive and figure out shortcut rules for inverse trig functions and logarithm functions. It asks you down here in 3.7 to do some reading. Now that we're in this whole remote learning environment, of course, you may want to do more textbook reading than you've ever done, and perhaps watch videos from the textbook as well.